Hi everyone, my name is Habi, and today I will present our work, HMQ, Hardware-Friendly Mixed Precision Quantization Block for CNNs. This is a joint work with Jennings and Arnon Netzer that was conducted in Sony Semiconductor, Israel. Quantization is a key method for enabling the deployment of neural networks on embedded devices, as well as for reducing their memory requirements and latency. Recent work has shown the benefits of using mixed precision quantization, a method in which the bit widths are not constant across the model. In this work, we introduced the HMQ, a hardware-friendly mixed precision quantization block based on the Gumbel-Softmax estimator. This block enables searching for hardware-friendly quantization schemes, specifically a quantizer that is symmetric, uniform, and with thresholds that are constrained to the power of 2. We demonstrated the use of the HMQs on modern lightweight networks. For example, in MobileNet V1, we compressed weights to an average of approximately 2 bits with an improvement of up to 11% in accuracy compared with other methods. Every uniform and symmetric quantizer can be parameterized by any two of the three parameters: threshold, step size, and bit width. The HMQ quantizer is parameterized by threshold and step size and shown in this equation. Note that the quantizer is well defined for any pairs of the values of those parameters. Also, in this work, we use the Gumbel-Softmax estimator, which is a continuous distribution that samples a categorical distribution and is differentiable with respect to its parameters, pi. Using the temperature parameter tau, the Gumbel-Softmax interpolates between one hot categorical distribution when tau is close to 0 and a uniform categorical distribution when tau is close to infinity. In this work, we use the Gumbel-Softmax to search for the quantizer parameters. HMQ block. The HMQ block is built on few basic ideas. The first is to restrict its solution space to a discrete finite search space. Each solution in this space represents a pair consisting of threshold and bit width to parameterize the final quantizer. In order to search over this discrete set, we represent each pair as a sample of a categorical random variable using the Gumbel-Softmax estimator. Additionally, we restrict the set of thresholds t to the power of 2 values. During training, we define the expected threshold and expected step size using differentiable functions of the probability distribution of the pairs and learn the quantizer parameters using standard SGD. Here we present an example in which the HMQ search space consists of two solutions with a constant threshold and two bit width options, 2 and 8 bits. In this figure, we show a smooth transition of the quantizer between the 2-bit solution on the left to the 8-bit solution on the right. Optimization process. Our loss function is built on the idea that during the search, once the target compression is reached, the optimizer is guided only by the task loss. To achieve this, we designed a loss function consisting of two terms: a task loss and an asymmetric compression loss. The asymmetric compression loss is equal to 0 once the expected compression rate reaches the target compression rate. In this figure, we show an example of the asymmetric compression loss as a function of the expected compression rate, with three target compressions: 10, 16, and 26. During training, the target weight compression rate is gradually increased. Here we show an example of weights compression behavior during search. Note how the actual and expected compression rates follows the target compression rate. At the bottom of the graph, in red, is the temperature annealing cycles of the Gumbel-Softmax estimator. For activation compression, we take a different approach, where our objective is to fit each tensor into a given memory budget. These objectives enable us to determine the exact bit width of each tensor implied by U and the number of elements of the tensor. During training, we gradually reduce the target memory budget U. As for thresholds, we take the same approach as with weights and use the HMQs with standard SGD. Experimental results. In our work, we compare results with those of other mixed precision methods on ImageNet classification tasks using EfficientNet B0, MobileNet V1, MobileNet V2, and ResNet 15. Here we show a comparison of weights compression with HMQ. We present state-of-the-art result in MobileNet V1 and ResNet 15, where we achieved higher accuracy with the same compression. Here we show a comparison with DQ, AJWQ, and AJWQ V2, where both activation and weights are quantized. We show competitive results despite the restriction to a hardware-friendly quantization scheme of our method. Finally, we show a Pareto frontier of all the network that we quantize in this work. The x-axis is the model size in megabyte, and the y-axis is the model accuracy. Additional results can be found in the paper. To conclude, we introduced a hardware-friendly mixed precision quantization block, HMQ, that utilizes the Gumbel-Softmax estimator. We used the HMQ to search for quantization schemes which are uniform, symmetric, and with power of 2 threshold. We showed state-of-the-art results using our method to quantize lightweight models on ImageNet classification task. Thank you for watching, and our code is available on GitHub.